Okay, I can start again this morning section with Professor Marcos Bregant from the University of São Paulo. He speak about instrumentation lab of HEPIC in University of São Paulo. Please. No. Maybe you need to put on. It's on me. Yeah.
Is it work? Okay. Okay. Good morning. First of all, thanks for the invitation. I'm very proud to be here. In some way, okay, something related to the previous presentation. We are this morning a lot about instrumentation and equipment. I'm here to present the work, the activity, instrumentation of a HEPIC group in University of São Paulo, USP. So, very short of look. So, what's HEPIC? What is this group? And then focus a lot in instrumentation. Talk a little bit about micro-pattern gauge detector, which is part of our activity. The readout electronics, which means SAMPA chip. And since I have a lot of questions about it already at the beginning of the week, I decided to devote a good part of the presentation about that and some other activity to show the general picture of our group. A bit of historical background. The Physics Institute of São Paulo has a quite a long historical record in experimental physics, starting with the nuclear group with the Pelletron activity. And basically, our group is a branch of the historical low-energy nuclear group of São Paulo. In the late 90s, the group started to interest in a bit the middle of high-energy nuclear physics, participating in BNL experiment, and then entering even in a STAR experiment. In all these cases, working both in the analysis part, physical analysis, but also in the instrumentation. Based on that, the group moved in the middle of 2000 to ELIS experiment. And then we also was changing with time the name, where HEPIC means High Energy Physics Instrumentation Center. Presently, the group is strongly involved in ELIS physics, and Marcelo Munoz will present some of this analysis, some of this activity on Friday. And from instrumentation part, in the last years, the group, with collaboration with a local polytechnic school, developed a new chip, new ASICs, to be used in ELIS gas detector. The group also activity in micro-pattern gas detector, is a member of RD51 collaboration, and is performing studies of better understanding the micro-pattern gas detector structure, basically a gem, and looking for application, even really application physics or other kind of use. And recently, the group of Physics Institute of São Paulo that was working in Atlas, was a different group, joined the HEPIC, and so presently HEPIC represent the whole community working in high energy physics, experimental energy physics at USP. I don't know the driver. Okay, who's the people involved? The group, especially instrumentation, is not extremely big, but it's not too small. We are a full faculty, full professor involved. Two of them having instrumentation as a main topic of research. We have university staff, a technician, which is a physicist, which is PhD, involved instrumentation and electronics. We are two very quite skilled technicians with expertise in electronics and detectors. Presently, we have two PhD students involved in instrumentation, two master students, and also several, okay, the number is fluctuating, internship students. What is in Brazil, it is called Iniciação Científica, che is an internship of graduation students we perform during their graduation. We have a strong collaboration with the engineering school, Scuola Politecnica da USP, especially due to SAMPA, but not only that, and with IPEN, which is the lab research in nuclear energy here in São Paulo, which is just on the backyard of our institute. So, having a quick look at what we are doing, shortly about micropattern gas detector. Okay, I was not aware how much people knows what is a gem. That's it wasn't in the before. It's really a thin layer of capton clad with copper, both sides, where it's very is drilled. We have a pattern of micro holes all along the surface. How it's working? You apply a strong electrical field on the two sides. This means you have you apply a strong voltage on the side. You have a strong electrical field inside the hole, where it can happen an avalanche. Doing that, you can a multiplier of electrons, as the name is saying. At the good point, differently for proportional chamber, is that after multiplication, the charge is not collected. In proportional chamber or in multi-wire chamber, the multiplication is happening close to the wire, where then you collect the charge and stop everything. Here, after multiplication, you can extract the signal, the huge number of electrons you produce, and do whatever you like. Go for direct readout, or what is usually the case, put a second layer of amplification. This helps a lot in having better stability and controlling the amplification of the system. This also implies study about geometry, because you have the choice of how many layers, how to put every layer, how every layer is made of. You can choose the pitch of all, and your gem stack will behave differently. And then you go for a readout, having the choice, depending on the use, to be a pad readout or a strip readout to have pure 6Y readout. To find the proper configuration, depending on the use, some study is needed, and this is one of a kind of research, of studies we perform in our labs. You have to have an idea when we have a prototype or a demonstrator or a small gem where to perform our all our studies. You need to handle that, and here you perform. You need you not need a clean room for this small object, but for sure a clean corner in your lab to perform that. All are around 50 microns, so dust can be problematic, should be avoided. We're also studying a different flavor of gas electron multiplier, which is the thick version. What is the gain? Okay. Using standard electronic board, it is by far easier to be produced. In some way, any company who perform standard electronic board is able to produce this kind of board. Performance are a little different, or a little worse, but depending on the use, the worst performance are more than compensated by the ease of use and having our object even more stronger. Here, just to make an example, this is a board was produced locally where we tested different pitch just to study how the pitch of the system is modifying the behavior, the performance of the thick gem. What are the kind of studies presently ongoing in our lab on this field? This is a part of simulation, just to investigate in simulation different ideas, different configuration. Having then the option, the purpose to produce a configuration which is slightly different and be studied experimentally in the lab. About application, people is studying the possibility to use gem detectors to provide colored X-ray imaging, so the possibility to have a detector which is sensitive at the same time to position, to make an image, but also to provide for each point the energy of the photon, and so make a color picture in X-ray spectrum. From one side, it's not competitive in terms of resolution with imaging made on silicon. It's not compatible with spectroscopic level silicon detector, but it can do at the same time. It can be very interesting to have an overview of an object. One application may be the preliminary study of a picture or archaeological piece of data. Also, we are studying the use of gem or thick gem as amplifying part for other kind of detector, depending on the sensitive part. One example we are studying is to use a boron 10 as a converter for capture neutrons to get charged particles that then are measured by a gem, and so having a neutron detector which is not anymore helium-3 based. It's just some example of what we are investigating that, but the message that we have a lab which has the capability to perform some studies on optimization with gem microparticles detector. Now I'm entering into the readout electronic part. After some discussion at the beginning of the week, I decided to go quite a lot in details at this point about the SAMPA chip. It's starting to be fast anyway. So, how we got involved in this SAMPA chip in the ASIC business? It came, first of all, it came from the need of ALICE to upgrade mainly the temperature chamber for a higher luminosity and higher interaction rate. Alice is moving from is moving this moment from multi-wire chamber to gem readout. Previous ASIC cannot read the output of multi-wire chamber, and also didn't have the capability to stand continuous readout. Our group got in contact with Polytechnic School here, and we said, we can do it. We have this crazy idea, but it worked. We manage, and so what we evolve is a chip, an ASICs, optimized for gas detector readout, basically gem, but not only. Quite dedicated to the ALICE use. We have to make a choice. Already ALICE is asking a lot of things, and the chip end up to be more or less general, but not completely, because it's not possible to, in a short time, to start thinking, including more feature on it. But already the requirement for ALICE were quite strong. The chip should be used for readout of both TPC, which is gem, negative signal, and the moon chamber. We still use multi-wire precision chamber, so positive signal. We asked to have a higher gain, two different gain for TPC, which are 20 and 30 millivolt per femtocoulomb, but also to have a higher dynamic range, lower gain for moon chamber, which is 4 millivolt per femtocoulomb. After that, okay, the noise in the order of 500-600 electrons for higher gain, and around 1,000 electrons for the moon chamber case. Also, peaking time are different for the case. For TPC, the use is 1/16 of a second. For moon chamber is 300. We can back later. Okay. So just to have an idea of the general layout of SAMPA, we have a amplifier, shaping, a DC converter, and digital signal processor. Still something really a dummy plot, just to have an idea, but every channel has its analog part, made to provide for every charge two different gain, and one gain, one different peaking time for positive charge. Every channel, SAMPA chip has 32 channels, has its own ADC. It's a successive participation ADC, 10 bits nominal, working at 10 megaseconds per second, providing NOB better than 9 bits. In this moment, is under development a version that can keep the same figure, is aimed to keep the same figure even at 20 megasamples per second. And then we have a digital signal processor, which is common for all 32 channels in some way, providing a different feature. Here going a bit listing them. First of all, providing a different kind of filter, aim to correct baseline fluctuation in variation, providing a tail cancellation, providing other kind of feature that compensate some under overshoot or some distortion due to readout, depending of the system. Then, okay, there is, of course, a logic, a hierarchy in all data, but skip. The different filters are in a logical sequence. You can activate the one you need. Each filter is hard-coded in some way, cannot be modified, but has some parameters which can be set. Has some register where you can change the behavior of the filter, changing some integration time or something like that, to adapt the filter to use. But the logic of the filter is hard-coded and, of course, cannot be programmed. About top-level configuration, it's possible to perform a quite standard zero suppression. It's possible to provide, to perform cluster sum and then send out just the sum of the cluster or area, if you like to call it that. With also some capability to apply Afron code for data compression. All the configuration are via I2C. There are standard JTAG option for testing before installation or to verify proper working. Formally, SAMPA is not, cannot be a radiation-tolerant chip. It's not. Nevertheless, some care, some attention was put to reduce radiation effect on it. No one of the inside circuit are radiation tolerant by design of the single element or single transistor, but several strategies in the overall logic was put in place to reduce radiation sensitivity of SAMPA. One example was aiming protection for EDAS or other part of memory. The readout offers different options. The output, the communication with SAMPA is via up to 11 E-links, each capable of 320 megabit per second. But depending on the use, it's not compulsory to use all of them. You can use less if your data flow is less. Even in Alice, TPC is using all the links. In case of main chamber, we are using cluster sum, zero suppression, and even daisy chain to reduce the data flow and can go further with the lower throughput rate. The balance of the data among channel is programmable, but is hardware. You decide how many channels to devote each links. It's not online load balance. There are different ways to use it in a triggered mode, in continuous mode framed, or either the possibility to work in direct readout mode, which means we are bypassing the digital signal processor. We are basically connecting directly the DC output to the outside, and then all the process should be done outside the chip. Okay, I mentioned here possibility to buffer this chain, the data DC serialization is possible up to 10 megasignal per second. since 32 channel, 10 bits, 10 megasample is 3.2 gigabit per second, and so 10 links are used with the data throughput, and 1 is used as clock for synchronization. And the form factor of the chip is packaged in BGA to have a small footprint. And okay, one message is that SAMPA is presently available chip, is existing already. Here's a picture of how is the die, which is 9 × 8 square millimeter, and the final version of the package chip, which even include serialization to help tracking it along testing and installation. Inside the QR code, we have the serial number, which identify in a unique way the chip. Sadly, due to the process, the tracking of the chip starts at this point. Here we have just information of the batch of the wafer inside, but we don't know the wafer or the position of the wafer of the chip. But in any case, the yield is quite good. For industrial point of view, is higher than 80% in terms of not working chip with a memory problem or with broken channel. Then for application, cuts above dispersion of gain or noise are put, and so basically 70–75% are considered perfect for installation, let's say. Here is some results to give an idea of performance of the chip. In terms of noise, here this is the case of a 20 milliwatt per femtocoulomb configuration. Here are an example of some samples, and looking how the noise is along the 32 channels, and basically there is no any pattern. So all 32 channels are quite equivalent. We don't have a pattern of noise inside the system. The distribution among different channels and chips is reasonably narrow, is in terms of 1 ADC units RMS, or we turn out to be 600 electrons, equivalent noise term. Other way to see it is very concentrated with very few outliers. Here the statistic is already quite high. Other important point is how noise is depending of detector capacitance, the capacitance charging the input, and we are above around 1,000 electrons with a detector capacitance around 20 picofarad, but the system is quite stable, and okay, the noise is increasing, but the chip doesn't have any problem to operate with detector capacitance of 50 or 100 picofarad. In terms of sensitivity or of gain, the full chip is quite linear for almost the full official range. It's possible to see how the residuals are inside a few millivolts till reaching 60 femtocoulomb in the gain of 30 millivolt, which is already more than 80% of the official dynamic range. So in general, the linearity is good up to 80%, 85% of the full range in all of the three configurations. One important point because is how the chip will behave in case of pile-up or high-frequency stimulation. And here is a lab test where one channel is pulsed always with the same value at a frequency of 1 MHz. Due to the first integrating part of the chip, what is important in the kind of test is the current, is the average current. So sending 20 femtocoulomb every microseconds is the same as sending 40 every 2 microseconds of 10 every 500 nanoseconds. So we choose this definition. You're supposed to see how up to 35 nanoseconds, so sending at 1 MHz 35 femtocoulomb for several tens of microseconds, the gain not changing, no saturation effects are happening. Moving in the range of 40, it's possible to see how there is the gain is going down, but then it stays stable. Okay, if we exaggerate, the charge amplifier gave up, it cannot anymore amplify and provide. A good point is even pulsing at 1 MHz, something with 50% of official dynamic range. Okay, we have a saturation effect, but after some recovery time, the gain comes back to normal. Okay, these are more or less the limitation, but we know it how it is. In case of ELIS, most of the time, in one channel which is coming are MIPS. Sometimes can be a burst of signals, but our bursts are quite short, are 5-10 microseconds. And so we match will be with a current that maybe will be around 10 nanoamperes in case of ELIS, in terms of charge coming. So at least in ELIS should be okay. This is the last version, version 4. Version 3 didn't have this capability, was saturating earlier and was corrected. A bit, okay, final overview more or less about SAMPA. Was its design was strongly ELIS TPC moon chamber driven, but there are several features which are quite general, end up to be a quite general ASIC for gas detector readout. It's providing basically 2.5 option for gain. The version available and validated operate ADC as 10 megasample per second. Even if you are studying the possibility to have a version working at 20. For the readout, depending on the use, different options are available. And okay, the limit of data throughput of the system is around 3.2, 3.4 gigabit per second, which is more than sufficient working at 10 megasample. Moving to 20 will means some data reduction should be provided already inside the chip. Just to see where people other activity, just two pictures, one showing one of the students looking and testing the chip, even possible to see the output of the front end. Here he was testing the test block, having only the front end without the ADC. People also is using the facility available at USP, which is Pelletron, to check sensitivity for single event effects, which is also a problem initially. One of the memory of version 2 proved to be quite sensitive to radiation, to particles, but being able to perform a chip scan, knowing the map of the circuit inside the die, and so being in close contact with the developers, we are able to identify the area of the chip which are extremely sensitive with just one kind of memory. Memories inside SAMPA are were not designed, were bought. We just changed the memory we put there. It's the same we already know the place that was not so sensitive, and now, at least for what should stand in any environment, should be quite safe to be investigated in a harsh environment. What will happen? A bit more, the part of people coming from Atlas experiment, who joined our the HEPIC group 2 years ago. We are also quite involved in electronics. Now we're trying to converge to have a more activity together, but we work in the trigger board and logic for the digital accelerometer. We are now in contact in some early study for high granularity timing detector, which means basically low gain average detectors. Very important point that after this when you join us, the group, the HEPIC in general, is even more strong, having gained 2 well-skilled and qualified technicians, which is also quite important for instrumentation and hardware in general. So, conclusion about that, okay. The HEPIC is the USP center, USP group for experimental high energy physical instrumentation. We are working both in the analysis, and on Friday Marcelo will talk about that. We are studying developing instrumentation and also possible spin-out application of what we developed. For instrumentation, the group steered the development of SAMPA chip and the validation of it. We are working in studying the physics, which is beside the micropattern detector, and trying to look for different optimization, different layout of the system, and also looking for the future for solution for next generation high energy physics experiments. Thanks for the attention.
Thanks for the speaker to show the art of experimental high energy physics in the University of São Paulo. I'm open for questions and comments. Yeah.
So you've said that your signal event effect tolerance is sufficient for the Alice environment. Can you say something what the Alice environment is? So how much radiation dose you expect?
The total dose is 100 of kilorats for full time. So dose is not a problem, never was a problem. Already the use of TSMC 130 nanometer technology was providing enough safety for total dose. About single event upset, we should look back at the exact number of limits for cross-section, and especially where is the threshold. Not a colleague from Norway performed really the study of linear energy transfer and what is the threshold of energy to induce a single event effect or upset in the system. But this number may not here at the moment.
Okay, thank you.
Okay.
Other comments or questions?
So the version 4 you have now, this is for the production version for Alice, for the DPC?
It's the produced version for Alice, who's already produced, is already being installed in the front-end electronics for TPC, and the amount of chip needed for the main chamber is going to be tested in this month to provide well-qualified chips, good chips for building the front-end electronics for main chamber.
Okay, so this is coming up then.
Yeah.
More comments, questions? Oh, I don't know. If not, thanks again, Professor Marco, for the presentation. The next speaker is Professor Tobias Stockmanns, I don't know my pronunciation, from Jülich. He spoke about PandaRoot, the simulation reconstruction framework of Panda.
Yeah. Sure. Let's see if you also get that. Yeah, sure. Yeah, thank you very much for the kind invitation and all the great hospitality we experienced here during our stay in São Paulo. And after you've heard about the hardware and also the hardware aspects of the PANDA experiment, I'm going to speak about the second part, which is essential if you want run such an experiment, which is the computing infrastructure. And I'm mainly speaking about the PandaRoot simulation framework we have developed to simulate and the PANDA detector and to do the readout, the reconstruction, and the analysis of the physics events we want to study there. So even before you start building the first hardware components, you need to have a software which allows you to determine the operation parameters for your experiment. So what are the rates you have to face? What are the energy depositions? What is the radiation dose your detector has to withstand? Then you have to optimize your detector layout. So is it better to put the layers of the microvertex detector close to each other or better separate them from each other? So already at the beginning of an experiment, you need to simulate the experiment in a quite high detail level that you are able to build it in the best possible way. You have to develop the reconstruction algorithms which will be used once you get the raw data. You have to develop the analysis tools and strategies, and you have to determine the performance of the PANDA detector for the physics channels you want to analyze. Also to convince the community that it's worth to build such a detector. You have to be able to reconstruct the raw data once the experiment is running. You have to perform the physics analysis, and you have to simulate of the expected event signatures that you can see if in your data coming from the experiment you see something you do not expect from the simulation you have done. And all this has to be covered in the simulation framework of an experiment. So this is a huge enterprise, and this is something we cannot do by ourselves, but we are doing this together with other experiments, and there's a base framework which was developed by our colleagues at GSI, which is called PandaRoot, and this was initially intended to be used by the FAIR experiment, but at the currently we have a huge user community there, and for example also Alice is using this framework as their basis for their O2 framework they're using. This framework, first of all, uses a so-called software stack of external software packages. The most important one here is Root. We are using Boost. There are different simulation engines like Xenon 3 or Xenon 4, and a lot of other software packages which are coming just from the external side, and these are all packed in this software stack. Then there is this main framework, PandaRoot, which is the base for all the others. There you have the testing facility, you have the geometry description, how this is handled is in there. There's a parameter conditional management for the parameter base, detector response, magnetic field, event generators. This is, or the interface to the event generators. This is handled by the PandaRoot base framework. And there's a quite new development on top of the PandaRoot framework, which is called Alpha. And I will say a few words about that in my next slide. Here they introduced a message queue system which should allow you to parallelize your software so that you are able to reach really high throughputs and high performance on multi-core machines. And this is the base framework, and derived from that is the framework we use for our experiment, which is called PandaRoot, and which will be the topic of my presentation. So I said these message queues are a very important new feature introduced in PandaRoot, and to explain you a bit what they are doing is they allow you to send data, which sounds quite trivial, but the point is that you have your input files, your online data, and all these lines here are these message queues, and you can send them to individual tasks, and these tasks can run on different machines. They can even be processed in different languages, so you're not restricted anymore to a C++ language. You can use Fortran, you can use Python. There are interfaces to almost 40 different programming languages, which you could all use when you want to analyze or simulate your detector. The other point is, if you look at such a scheme, each of these blocks here is individual. So it runs for itself as a process, and you have immediately a multiprocessing environment. And inside this process, you can use all these other tricks you can do, like multithreading, so to even speed up this more. But this also means that you have to go away from a sequential approach usually used in software to think more about a data flow model, about how many of these tasks you need to process things. You have to think about where are bottlenecks. For example, if you have here one task which is dependent on two others, is this task here fast enough that it can process all those things? So this is something with introducing these message queues and this multiprocessing, you have to also change a paradigm for your software environment. Yeah, for sure. This is just, you could use whatever you want. That's what is meant for that. No one really wants to use Windows there. Don't worry. The more important part is here the GPUs. And so GPUs is really an issue because they offer much more parallelism than standard CPUs, and they can really make a difference, especially when looking into tracking aspects or something like that. So here, this is more important than this Windows stuff. Forget that. All right, now coming to PandaRoot. So if you think about how this simulation is done, then you start in a sequence of steps you have to do to really fully simulate all the things you want to do. So you start with an event generation. So this describes the effects when, in our case, the antiproton hits the proton? What physics is going on there? What particles are generated there? And these primary particles then put into the propagation, which is basically, in our case, Geon 3 or Geon 4, and these particles are sent through the detector. All the detector effects are simulated, all what could happen if a particle hits a detector element. This is going on in the propagation stage. Then comes the digitization, and the digitization is very important to describe the effect of your electronics onto the, let's say, deposited energy in your sensors. And the goal has to be that after this digitization stage, you have a data stream which looks exactly the same thing like you will have later on in the experiment. So that this basically is indistinguishable if the data is coming from your experiment or from a simulation stage. Then this goes into the local reconstruction where, for example, ADC values or channel numbers which have been hit are then translated into physical data like positions of or energies. Then this goes into the global reconstruction where tracking is in, particle identification. Then comes the event building and the last stage analysis. And I will go through all these stages on my next slides. So event generation. Event generation, we have several different so-called event generators. Then the most important one for us is so-called going to these, and then you can even define further on how these further decay. And then you can extend this by individual decay models, and here's an example where this EVT generator was extended by Dalitz model where a D sub S is decaying in 2 kaons and 1 pions, and this is coming out of the simulation, and this fits nicely with the experimental data. Signal is one thing, background the other, and for the background we have basically 3 different generators. The first one is called a so-called dual parton model-based background generator for antiproton-proton interactions. The second one, based on UQMD, is antiproton-proton on nucleus interactions. And there's a quite new development which is called FTF generator, which is basically able to handle both antiproton-proton-proton or antiproton-nucleus interactions, and this is also used in Geon 4. And for testing purposes, there's also a thing which is called a box generator, which is basically a particle gun. There you can tell, shoot a pion in this direction with this energy through your detector and see what your detector does out of that. After that, you have defined your primary particles, but you will need to know how these primary particles move through your detector. Which energy is deposited at which detector element, which detector elements are hit. And for these, we are able to use basically Geon 3 or Geon 4, and they are connected via the so-called virtual Monte Carlo engine, which makes our software completely independent. If we use Geon 3 or Geon 4, this is just a string at the beginning, and we can use all of them seamlessly without any problems. So another important point is that also the same geometry description is used in the propagation stage and later on the reconstruction stage, and all this is handled by Root itself and doesn't rely on the different engines from Geon 3 or Geon 4. Geometry is an important point. If you want to build a detector, here's the CAD model. You want to be sure that also what you simulate is the same what you've done. And therefore, we put a lot of effort, especially in the last year, to come up with realistic detector descriptions. And here are just some examples of the subdetectors inside PANDA. So here you have, for example, the solenoid and dipole magnet with the dipole coils here. Here are the different central detector calorimeters. Here's the Dirk and the Cetal detectors, the gem detectors, the straw tube detector, which sits here, and the last one, this is the smallest detector down here, is the so-called microvertex detector. And for example, this part here consists of 70,000 individual elements inside the simulation, even describing single SMD components, because this sits directly around the interaction point, and all the material which is there has a huge impact on the performance of your detector. And this is how the complete PANDA detector looks like in the simulation. You can see here the beam pipe going through it. Here's the interaction point, and there are all the different subdetectors of the forward and the central spectrometer. So after you know which detector elements have been hit and how much energy there was deposited, you have to do the digitization. I already said that this stage is important to get a data stream which matches to the data stream coming later on from the experiment. So 3D space points are translated into channel numbers, deposited energies and ADC values, adding noise, adding inefficiencies, charge sharing with neighboring detector elements, dead times, and electronic properties. This all is part of that. And I've put here 2 examples of the simulation. So this is an avalanche simulation of the muon detector. You can see here, this is the wire sitting in the middle. And here you see how this avalanche from an incoming particle evolves around this wire position. And down here is another example. This is an EMC waveform. You can see here 2 hits, and there you have some noise in between. So this is all taken into account in the simulation software. In the reconstruction stage, we have subdivided this into 2 parts, reconstruction 1 or local reconstruction. There, you take this ADC values you just create in the digitization stage, and you want to come back to physical values. So here, the translation from an ADC value to an energy, calibrations, clusterization, and reconstruction algorithms are part of this local reconstruction stage. And here's just an example where you have a clustering algorithm. So you have this hit pattern here, and you look into circles around the midpoint. If there are other pixels, in this case, being hit in the neighboring, and then you just combine them, and then you have a local cluster which was created by one particle going through that. We have various different algorithms implemented for each subdetectors. We try to compare them and use them for test beam data so that what we're doing here in simulation really matches with the real experiment. And as I said, PandaRoot is also used to reconstruct test beam data. For the global reconstruction, there the different subdetectors are combined. There's tracking, PID, and event building done. And now I'm coming to a larger section about the tracking inside PandaRoot. So what does tracking mean? So I have here an example. Here again, the geometry of the central spectrometer. Here you have the antiproton beam coming in. Here was an interaction with the target. And all these points here are detector elements which have been hit and which have created a signal. Well, this is how it looks like. And you can see this is now the picture if you look in the direction of the beam. Here's the interaction point. And because we have a solenoid magnetic field, these tracks look here like circles. Basically, they are moving on helices through the detector. And tracking now means that you identify the points which belong to one track, and you determine the track parameters. So basically, the position where the particle has started and the momentum of the particle. And here's a so-called time-based simulation of the microvertex detector in the inner part and the straw tube tracker. And you can see here that sometimes there are points flushing up. This is the hits coming from the microvertex detector, and this is surrounded by these circles from the straw tube detector. The straw tube detector uses drift time information, and it's a quite slow detector. So there you have 250 nanoseconds drift time, while the microvertex detector has a time resolution better than 10 nanoseconds. And in continuous data stream, this is the picture you get, what the detector and also your algorithms have to digest and find those tracks going through your detector. So what are the steps? The first step is the so-called pattern recognition or track finding stage. Here you have the group, the hits, which belong to the same track together. Then you make a pre-fit. This is a fast evaluation of the track parameters, usually based on a simple model, how your track behaves in your detector. And then there comes the third stage, which is based on the Kalman filter. So there you do the precise fitting of the track parameters. And this takes into account all the material effects you have, all the energy loss you have if your particle goes through a detector element. So after that, you have the most precise track information. And the last stage is to propagate the track parameters to the point where they are needed. So going backwards to the interaction point, or going forward if you want to connect tracks with, for example, the electromagnetic calorimeter. This is the propagation and the extrapolation stage. So for the track finding and fitting, we have a so-called offline barrel tracking. So this using local pattern recognition in the straw tube detector, shown here. So you have here the tracks. Here you have the isochrone rings of the straw tube detector, and they belong together. And then we also do a standalone pattern recognition in the microvertex detector, and then we combine these two. And after that, we extrapolate the hits from these two detectors onto the gem planes, and then we add the gem hits which match to these tracks so that we have a complete description of all the points belonging to a track, and then we add a Kalman filter later on. For the forward tracking, we use a different approach based on a so-called cellular automaton. Here we have planar detectors before, inside, and outside, or behind the dipole magnet. Here you can see tracks going through this part, and you see here are the stations before and after the dipole, and these are the stations inside the dipole. And this cellular automaton groups these into layers, and then he connects each point of one layer with each point of the second layer, which is shown here in the segmentation stage. Then they are making a weighting of these segments based on the track model behind, which are possible tracks, which is down here with these counters. And then the track candidates are selected based onto the length of the track segments, or the longest track segments from going from the beginning to the end of your detector. And only the longest one, they are surviving, and then you check them, for example, with the chi-square method to define if the track is now going in this direction or the track is going in this direction, and then those two tracks here are surviving, which are the real ones, and not those two here, which are the fake ones. This works pretty nicely. We have a 97% track finding efficiency, and this is also an algorithm which could be used in an online world where you have to be much faster, because there you have to do the track finding essentially with the same rate than the data is produced in your detector. After this fast fit, then we are doing a global fit. So here you can have the two magnetic systems we have inside PANDA, the barrel part with the solenoid field and the forward part. And you see that these two different magnetic fields makes it difficult, because you essentially have two different tracking environments and different track behaviors. Here you have the helices here, and then you change the magnetic field, and then you have the hyperbola movement inside the dipole part. Then you have different track or hit types. You have more or less planar hits in the MVD and the gem, and you have this tube plus drift time information in the STT and the FTF parts. So with this pre-fit information and the detector hits, we go into this Kalman filter, which is based on a global development called GenFit. And this Kalman filter then uses a track follower called GNI to predict the position of one of the tracks on the next detector plane, and this is then taken all together inside the precise tracking based on this Kalman filter. How good this works is shown here on this slide. So we have track finding and fitting working for the central and the forward spectrometer. The Kalman filter is used as the second stage developed by the University in Munich. And we have efficiency above 90% for beam above 3 GeV. You can see here this is a momentum versus efficiency, and there's a drop of efficiency if the momentum of the particle gets too low, but this is a topic we are still working on to improve that part. And here on the right side, you can see the momentum resolution. So with increasing momentum, we have a worsening of the resolution, which is expected because then the curvature of the tracks gets less. But in general, we are for most of our tracks in the region of a few percent track momentum resolution for that. For the parts where we have an antiproton beam below 3 GeV over C, then the magnetic field is reduced, therefore the curvature gets higher, and therefore also this resolution gets better. As I said, online track finding is a very hot topic there. You have to really process the data stream coming from the detector with the same rate than it is produced. We are speaking here about 200 gigabyte per second of data in the high luminosity mode. And we have to come up with this dedicated hardware which is able to do the track finding. And this is something we are working on. We have tested an FPGA approach or a GPU approach with different algorithms here, and I will pick out one of them to show you what we have done there. This is a performance measurement of a HUF approach where we tested different GPU versions. So this is a consumer grade card, GTX 750. This is a high performance card. So you can see here that this high performance card is about a factor of 2 faster than the consumer grade, but it's also a factor of 10 more expensive. So one could think about using consumer grades as long as NVIDIA allows us to do that. And I forgot to say something. So inside our simulation software, we have a switch where you can just say, use the GPU version or use the CPU version, and this is all you have to do to incorporate the GPU if you have one in your system and you have the code developed for that. So just an example how one of these fast algorithms works like, and this is something we have came up especially for the straw tube detector, and this is a so-called circle HUF transformation. This is a simplified picture, so in the middle part, this would be where the microvertex detector is sitting, and then you have here a simplified straw tube detector, and these gray circles here, this would correspond to a single straw, and this red ring here would correspond to a single hit inside one of these straws. And the first thing is that you can just, for a given momentum or given radius of the circle, you can calculate all the rings which go through the interaction point and are touching this isochrone hit here in one of the straw tubes. And if you do that, you come up with 4 possible combinations of these rings, and these crosses here are the midpoints of these rings. If you do that for many different possible momenta, then you have all these circles here, and these crosses are all the midpoints of these circles. And if you calculate this analytically, you can see that these midpoints are lying on a hyperbola. So each point of this hyperbola gives you a track which goes through the center or the interaction point and is tangential to the isochrone you have in this hit. One hit doesn't help you much, but if you take 2, or if you take more, then you see that you get points where all these lines cross. So this point here is a point where a track goes through your midpoint here and is tangential to all the hits up here, which belong to one track. For sure, you don't have one track, you have many of them, but if you then do all these calculations, you see you have one high point here, one high point here, and you have immediately done your tracking by just doing this in a parallel way. And the big advantage is that you can do all these calculations in a parallel way. Each of these hits could be run in a single process and can be processed there. How good this works is shown here on an example. This is a background event. Here you have the interaction point again. These are the hits and the circle of the tracks, and here is such a HUF transformation. This is what the detector sees. These highlighted points here are the points which have been correctly associated to a track. And okay, it's maybe a bit hard to see from the back, but these blue and red circles are then the predicted circles coming from this HUF transformation. You can see that this blue ring here and this red part here nicely fits with the tracks flying through your detector. Okay, that was tracking. Now we come to the next part. After you've found all your tracks, the next thing is to do particle identification. And this is the picture you've already seen from Tassos with all the different detectors which contribute to particle identification. So even the tracking detectors down here, MVD and STT, they measure the energy loss per distance, DDX, and this also contains PID information. We have dedicated particle identification detectors, like here time of flight detectors in the barrel part and the forward part. We have the Cherenkov detectors, you have the EMC structures which measure the shower shape, and we have the muon layers down here where you have the number of layers versus the number of hits. So you have a various different type of detectors. They measure the type of your particle with different resolutions depending on which energy regime you are. And you have to somehow combine this information. So that's shown here. This is the microvertex detector. This is the DEDX for 3 different particle species versus the momentum. And you can see, for example, above 1 GeV, you can forget the microvertex detector because there everything is overlapping. Oh, sorry. But if you are below that point, you can start to distinguish here a proton from a kaon or a pion. So if you have a DEDX at 400 MeV over C, which lies here, then you have most probably a proton and not one of these others. The same is true here for the straw tube detector, where you also have these bands. In the Cherenkov detector, you don't measure the DEDX, but the opening angle of your Cherenkov cone, and you have comparable bands down here. But they work better for higher momentum. So there, they are not suitable for low momentum particles, but more for high momentum particles. The muon detectors, you have the number of iron thickness which was crossed. And for the EMC, you have all these different parameters you can use to describe the shower shape and come up with patterns which are unique for certain particles. So you have all this different information. The question is, how do you combine that? And the first approach we are using is based on the Bayesian theory. So what we are doing here is each of these subdetectors calculates probabilities for that this particle is an electron, a muon, a pion, a proton, or a kaon. And if you then multiply all these probabilities, you come up with a global likelihood for that. And if you then weight that with the flux of these particles, then you have an overall probability that you have found a certain particle species for a track going through your detector. In addition, which is work in progress, we want to use also machine learning approaches. And this is something where we have trained, on the one hand side, a boosted decision tree, on the other side, an artificial neural network with all the different measurements coming from the different subdetectors. And what you can see here is the so-called confusion matrix. So here on the diagonal band, there you have the true particle species versus the predicted particle species. And if you have high numbers here, then you have done a good job. And everything which is on these side bands means that you have identified something wrong there. And you can see here that the boosted decision tree is slightly better than the artificial neural network, but this is still work in progress, and we reach here values above 90% for electrons, muons, and for the others we are around 80 to 70% particle identification performance for this machine learning part, which is slightly better than we achieve with our conventional Bayesian approach. That's a drawback of this machine learning stuff, that you don't really know why. Why. So that's something, as I said, it's work in progress. We still have to investigate that and try to understand why the performance here is worse. And okay, you have protons which are comparable more in mass. You have pions here, but kaon-pion separation is always an issue. So time-based simulation is one of the special topics of PANDA. The reason for that is that our signal and our background events are so similar that we cannot use the so-called hardware trigger, which is usually done by LHC experiments. There you have, for example, the muon chambers, which are fast. You continuously read them out. If you see muons, you say, this has to be interesting. Let's get the data of all the other subdetectors, but not before. So you only look on a very small part of your detector continuously. And only if you see something interesting there, then you take the data of the rest. That's something we can't do because we don't have dedicated detectors which could tell you this was interesting. So we have to take all the data stream, everything which comes from our detector, do a complete analysis of that part to say, this is something we want to keep, or this is something we want to throw away. In PANDA, we don't have bunches. So we have a quasi-continuous beam which hits or interacts with our target material. And how this looks like is shown here. This is a time difference between two consecutive events in our detector. The mean value is 50 nanoseconds, which corresponds to the high luminosity case of PANDA. But you can also see that you have a Poissonian distribution, and you have a very high probability that you have two events which are so close in time, which is much lower than this 50 nanoseconds. So you need to have a very good time resolution of your detector in a way to disentangle two events which are close to each other in time. The raw data rate we have is, as I said, 200 gigabyte per second coming from the detector. And we have to reduce that by an order of 1,000 to go down to something like 200 megabyte per second, so that we restrict our permanent storage capability to something like petabytes per year. This means that we need to use the so-called online event filter, and that's something we are also working on at the moment, how to do that in a proper way. And again, this is how tracking looks like for a single event. And this is how it looks like if you go to this time-based event. And we modified our simulation stream that we can deal with this time-based simulation, and we modified root in the way that you don't have events separated, but that you can simulate pile-up events, that you can simulate different time resolutions of detectors in a proper way. And one way how one can disentangle those events is if you just look on the data stream. This is a microvertex detector, and each of these red bars here corresponds to a hit and a timestamp of that. And because the time resolution of the microvertex detector is in the order of 10 nanoseconds, you can see here clusters. So these cluster here corresponds to one event, and these are 5 hits inside this one event, and this is the second cluster, a third, and a fourth. If you look here for the straw tube detector, which has this huge time resolution of 250 nanoseconds because of the drift time, you cannot disentangle those anymore. So what you have to do is you take the time information from the microvertex detector, and then you take all the hits which could interact with these here inside this package, and then you have to analyze them and just let them survive, which have hits in the STT which match hits to the microvertex detector. And down here is an example where such a separation by these gaps between the data stream was done for the gem detector. Here's what was simulated. Each different color means it's a different event. And this is what has been reconstructed. And there you can see most of the times it works quite nicely. But because of the Poissonian statistics, you also have those clusters here where things are very compressed to each other. And this is where this simple method is not possible anymore to disentangle those parts here. But if you combine, for example, these detectors here with tracking detectors with resolutions of 10 nanoseconds with time-of-flight detectors, which have resolutions in the order of 100 picoseconds, then you can also disentangle those events here, which have been merged together by these slower detectors. The last point I want to speak about is the PANDA analysis. This is what comes after you've reconstructed all the detector data. This then goes into a PANDA analysis class, which distributes this data to a package which is called row. And this row package provides you all different kind of filters you have to use to do your analysis, and also tools which is able to handle the combinatorics and is able to handle lists of different particle species and combine them into the analysis chain you want to do. So the row is a small framework to handle particle candidates. It handles combinatorics, lists, and selectors. And it has a so-called row tuple, which allows you to put this information from the several tracks inside your root tree, and you can use this tuple approach here to do your analysis there. PANDA analysis is the interface between for the reconstructed detector data and row. It offers you pit selectors and pit probabilities. It has the possibility to interact with our particle propagator, and it also gives you access to the Monte Carlo truth information, and it allows you to do complete decay chain matching. So what does it mean is, if, for example, you have antiproton-proton going to d mesons, then having kaons and pions, this not only looks if the pion you have reconstructed was a pion in the Monte Carlo truth list, but also that this pion was coming from your D, and this D was coming from your antiproton-proton system. As I said, we have different fitters inside. We have vertexing fitters. This is a point of closest approach finder. There's a fast vertex fitter. We have a precise vertex fitter. There are kinematic fitters, which allows you to use mass constraints, foresee constraints, momentum and energy constraints. And we have a tool which is called the tree fitter, where you have all the complete decay tree inside this package and all these constraints you have applied here in a single way applied at once, so that you have a complete chain fitted in one go. And there are different tools which allows you to do this analysis in a fast and user-friendly way. For example, this quick analysis, there you have to just give a text string which tells you what decay you want to analyze, and then basically everything is done automatically in this quick analysis stage. And here's an example of an antiproton-proton reaction going to this Ds. Then you have here the 1D going to a KK pi or a pi decay channel. This is the so-called tag mode. And this other D is going to a semi-leptonic decay with a lot of, with electrons and electron neutrino even and eta. This eta decays further onto pions and photons. So here everything is in. You have a lot of charge pions, you have charge kaons, you have photons, and you have missing energies coming from this electron neutrino. And down here on the left side, you see the reconstructed mass distribution of the D, where you have first all particles in, then you do a vertex constraint fit, which reduces largely these sidebands with the background data, and then you have a Monte Carlo constraint fit onto the mass, and then you just leave here not the constraint fit value, which would be a delta peak, but what just survived this fit. And then you can see here, this is the reconstructed D in this reconstruction chain. And here's two examples of the vertex resolution of this eta. In X direction, we have here a vertex resolution of 400 micrometers, and in the Z direction of 560 micrometers. So with this, I come to my summary. I hope that I could show you that root and fair root are the basis for the PandaRoot simulation framework. We are currently making a transition to this message queue approach, which allows us to make a very flexible online taking system, but this is a major enterprise because you have to touch all the different algorithms developed inside PandaRoot. We have different event generators, particle propagators available to simulate the physics channels and the background of interest for Panda. All the detectors are implemented in PandaRoot with a varying level of detail. Tracking is available, but needs to have more optimization, especially for the online part. And we've implemented time-based simulation to do the difficult event building and also the selecting process in Panda. Thank you very much for your attention.
Thanks, Professor Tobias. Now start open to questions, comments.
Hi, I have two questions actually. One of them is how big is what is the size of the PandaRoot team? How many members? How many?
That's varying because you always have students which are working mainly on maybe hardware work, and then they are also doing some software development for that. We have, as core developers, 4 people, which is me as a computing coordinator, my deputy, someone who's responsible for the analysis part, and another one who's responsible for the offline large data campaigns. And then we have about 10 people who are also working not on the core part, but on different detector components and that. I forgot one who is working on the tracking part. So we have, for example, 2 students who are working on the conventional tracking, and we have another 2 students who are working on machine learning-based tracking.
Okay, and the other question is a little bit technical. So you said that you can use whatever transport simulation you want, right? You can choose GN3 or GN4?
Yes.
So this, I assume that you have, so your geometry made someone else. So where do you do your geometry? And
Root.
You use TGeo.
We use TGeo, the TGeo manager, and this is interfaced into GN3 and GN4 via this virtual Monte Carlo system. So this is not developed by ourselves, but this is part of this PandaRoot package.
Okay.
And you just have to type in Geon 3 or Geon 4, and then you have the different engine they are running.
Okay.
It's very good. We also had Fluka, but then there were licensing issues, and we're not allowed to use Fluka anymore, which is a pity.
Okay, thanks.
More questions or comments? Yeah.
So you said one of your first slides that you used GPU computing. I'm not sure if I understood. Why do you use only in the last task? Why is it so CPU demanding or GPU demanding? Why do you not use it in all the processes?
Because GPU development needs a kind of special skill sets. It's a bit more difficult to do that. And we started with CPU development, which gives you all the flexibility to have. And then we picked out those tasks which is the most demanding one. If you look into the processing time, which is the one which takes the most time, is really tracking. And therefore, we picked out tracking to start with seeing how much we can gain from a GPU approach there. And we saw that this is something where we can really benefit from using GPUs. The other point is GPUs have a problem if you have a lot of the ratio between the data sending and receiving to the GPU and the processing time is so that you don't do enough on the GPU. You really have to get it running all the time, and you have to handle the data flow to the GPU in a proper way. And if the tasks you want to do on the GPU are too small, then you don't benefit from that, because the transporting of the data costs you so much time that you don't gain from all these massive thousands of kernels you have inside the GPU. Okay. Therefore, we concentrated on tracking, and it works there, but still it needs optimization. And for sure, other parts could be taken into account, but you have to really see where you gain something by doing this extra overhead using the GPUs.
And for communicating with the GPU, you used one of the available libraries, or Panda has made one of their own?
No, we use available libraries. So we use CUDA. For the NVIDIA part, and we are also looking into other things, but mainly it's CUDA because this gives you the best performance at the moment.
Okay, thank you.
More questions or comments? If not, I can close this morning section. Thanks all speakers. And remember, 3 o'clock afternoon return. That's not a problem. Yeah, I can do it. I will reduce the amount. No, it's not just we are not doing